Good morning, grade 12, and happy Monday. Let me see. First of all, I would like you to make sure that before you watch this video, you have watched the first one, which for today, which is a titration video, me actually doing a titration in my kitchen. It's about 30 minutes long, and I know that should be the max for today, but this is just following up with how you do calculations. So I'm going to try and talk your way through this one relatively quickly. But the two do go hand in hand, okay? Secondly, thank you so very much for those of you who passed in credit number 3. I really appreciate that. I am working through them. As I've said before, it's a real challenge with this team system to mark them, especially if they're photos or I have to download photos that are inside out and upside down and so on and so forth. It's very challenging for me because I can't mark on them per se. So it does take me a little bit longer, but know that I am marking them and I am recording those that have passed them in and so on and so forth. And I will be sending you back my solution set so that you can keep that for your notes for reference for later so that you can check with your own work and see where you went right or wrong and so on. Okay. So thank you for that. Credit number 4 is due this Wednesday. If you need any help with that, just reach out to me and we can set up a Teams time today or tomorrow or both. Okay. You are doing awesome. For those of you heading to post-secondary in the fall or those of you heading to post-secondary next fall and you're concerned about whether or not you have the curriculum required for the chemistry, I can guarantee you, you will. We are working very, very good at matching up the curriculum. You are missing out on time with me in the classroom practicing. I'm giving you lots of practice, but just not with me by your side. You're also missing your own hands-on work in the lab. I'm still doing the labs for you, and you're able to see them, thus with the buffer and the titration lab, and with the collision reaction theory when we did those labs in my kitchen with the Alka-Seltzer tablet and all that. So you are seeing the lab, you're just missing out on doing it yourself. So I am very pleased with how you are progressing, how we're getting through the curriculum. Just keep at it. We're almost there. June 12th will be here soon enough. Okay. All right, let's move on. Worksheet number 6, pH curves, can be found under the Files tab on Teams. Now, I did not ask you to do that worksheet. All I asked you to do from that worksheet was this question, question number 5. This was in Friday's notes, and in Friday's notes, I had the answers all blocked off. But that is from worksheet number 6, question number 5. And again, the entire worksheet Q&A can be found on Teams. I suggest that you look there and you try and work your way through that worksheet for extra practice with theory and whatnot. So this one is just showing you, although there are 2 vertical drops shown on this pH curve, there's only 2, there's 2 vertical drops, so that means 2 quantitative reactions, even though we're discussing sodium phosphate, which has room for 3 proton transfers and a 3 VO4, but only 2 of those transfers are quantitative. So that's why we only see 2 of those vertical drops, and that's what's explained here in the 3 reactions. So to get these 3 reactions, I wrote out sodium phosphate, comma, HCl, comma, water, just like your last assignment, and I broke it up into its entities, chose the strongest acid, strongest base. That's where I got the first line. And then, because I was using sodium phosphate, I know that the next time through, all of the sodium phosphate is gone, and instead I just have this ion to list within my entities, and so on. Anyway, very important question to have gone over, so make sure that you do that. The other homework you had on Friday were these 5 questions. I'm not taking the time to go through them. I think they are pretty straightforward. So you can certainly pause my video, look at my answers, compare with yours. And if there's anything you don't understand, please reach out to me. Teams, Remind, email, whichever works for you. There's question 3. Again, it was just the 5-step method, listing out your entities, telling me if they're acids or bases. And it does say here quantitative, so that's how I know they're both single-headed arrows. Just talking about a buffer and then what happens in an acetate ion buffer. Okay, all right. So now let's get to today's lesson. Today's lesson, I want to go over 2 questions. That's it, just 2 questions. And then I'm going to ask you to do a third one for homework, okay? So first of all, we're in the area or topic of titrations. And in order to use that titration to determine an unknown concentration, we're using what's called solution stoichiometry. Now, the tail end of grade 11 chemistry, you would have done mass stoichiometry. And if you had me as your teacher, you would have remembered mass, moles, mass. And so that's when we were starting with a mass, we converted it to moles, then did a mole ratio, and then went back to mass. So that was for what we call mass stoichiometry or gravimetric mass stoichiometry. Sometimes instead of starting with the mass, we start it with a moles. Sometimes we start it with volume, okay? And sometimes we ended up with volume, or maybe I asked you to stop at moles. Regardless, that's what we did in grade 11. Now, some of you might have had another teacher who would have taken you a little bit further and did some solution stoichiometry. I never have time to do that at the end of the year, but some of you might have done this already. So solution stoichiometry is just when you have the concentration of one solution and you're using it to find the concentration of another solution. And in order to get that data, you do titrations. Now, I think the best way to explain it is actually to go through an example. These are the steps that are going to help you with every single question. First, you must have a balanced chemical equation. You must then go convert from given to moles, do your mole ratio, and then go back to concentration of volume, whatever it is you're asked for. So again, very similar to what we did with mass, moles, mass, except instead of starting with mass, we're going to be starting with a volume or a concentration, okay? So if we just look at this first example here, solutions of ammonia and phosphoric acid are mixed together and produce ammonium hydrogen phosphate. What volume of the ammonia is needed to react completely with 1 liter of the phosphoric acid? So again, if we look at our steps, the first thing we need is a balanced chemical equation. Please pause this video now, take out your own paper and a pen, and copy and do this as I do. It's going to make a lot more sense if you follow the steps with me. So start off with your balanced chemical equation. That's what I have down here in black. Copy that down. The question they tell you, it's ammonia. And remember, ammonia is NH3. If you forget, it's on the back of your periodic table, lower left. It's a common reagent. You're mixing it with phosphoric acid. Remember, phosphoric acid came from 8 phosphate, and then you get ammonium hydrogen phosphate. Okay, now, after you write down your balanced chemical equation, fill in your given. So it tells you 14.8 moles per liter of ammonia. So I used red and I put 14.8 moles per liter. Now that's the exact same thing as uppercase M, same thing. And then I'm looking for volume of ammonia. So I put question mark liters with the ammonia. Then they tell me I have 1 liter of phosphoric acid. So there's my 1 liter of phosphoric acid, and then 12.9 moles per liter of phosphoric acid. And again, I can put that as molarity. Okay. Now, when we go to do our calculations, it might be a little bit easier for you to visualize if it's in moles per liter. So I will leave it in moles per liter just to help you with your boxes. Now, step 1 is always to convert the given to moles. And this is a formula we could use, or we could also use boxes, okay? If you look at this formula and you want to get moles, what you're doing is rearranging to get that N by itself. So you're taking volume times concentration. So when I look, what do I know the most about? I know the most about phosphoric acid. Do I know its volume? Yes, 1 liter. Do I know its concentration? Yes, 12.9. So if I multiply those two together, volume and concentration, I get moles. Great. That was step 2, convert given to moles. So I'm going to do that in boxes. Okay? Volume, there's my volume, 1 liter. Concentration, 12.9 moles per liter. Now you can see quite clearly how the liters cancels with the liters. Okay, so again, what did I do? I took my given and I multiplied my volume by my concentration to give me moles. Now in grade 11, we went mass, moles, moles, mass. Here, we're trying to find, we're using the concentration and volume to find moles. So we're at the mole step. What comes next after moles? Mole ratio. Okay, so this is where we look at our chemical equation, and what we're going to, the unknown, goes on the top. So this 2 is where I'm getting this 2. All right, and then the 1 that's assumed to be in front of the phosphoric acid is where I'm getting this 1 down here. Okay, so 2 on the top, what I'm going to, my unknown, and 1 on the bottom, what I'm coming from. Okay, so I converted to moles using my given. I did my mole ratio. Now they're asking me for volume, so I want the V all by itself. All right, so in order to do that, if I have moles on the top of ammonia, I want moles of ammonia on the bottom, and I'm going to volume, so I want liters on the top. So all I've done is taken this 14.8 moles per liter. And again, take note, these moles of phosphoric cancel with these moles of phosphoric. If I want this moles to cancel out, so I'm left with volume, I need to put moles of ammonia on the bottom. So that's where I'm getting this 14.8 moles per liter. So now moles of ammonia cancels out, moles of ammonia cancels out, and I'm left with only units of volume. And I take my handy dandy calculator and I multiply all the top and I divide by the bottom product. So 1 times 12.9 times 2 times 1. And then press equals. And then press your divide symbol. Oh, this is going to take me a little bit of time to find it. So maybe I'll just, if this doesn't work, we'll just give up for a second. There we go, divide symbol. Okay. So multiply all the top, then press your equal, then press your divide. Now I'm going to tell you to open your bracket here. You don't need to with this particular example, but you will in others. So it's a good habit to get into. And then close your bracket at the end and press equals. Okay, and that's going to give you 1.74 liters of ammonia is needed to react with 1 liter of phosphoric acid. Okay, so again, pause, rewind, whatever it takes to help you better understand that. So this first step, we're converting to moles, then we're doing a mole ratio, and then we're going to whatever they've asked for. In this case, they've asked for volume, and for volume, if I were to rearrange this equation, Control X, there we go. This is what volume looks like. Volume looks like moles divided by concentration. So that's why I have concentration on the bottom over here. Okay. Second example of 2. This is most similar to what we're doing with respect to the titration. Several 10 milliliter vinegar samples were titrated with standardized 0.582 molarity solution of sodium hydroxide. Now this is very similar, as I said, to what I did in my kitchen for you. We didn't use 10 ml samples of vinegar. We used 10 ml samples of sodium carbonate, okay? Um, but the calculations that you're going to do before Wednesday are going to be very similar. So instead of using vinegar, as I said, we used sodium carbonate, okay? And they were titrated with a standardized solution of sodium hydroxide. You know what? It might be a better example if instead of using this, I put in the ammonia here. Okay, so that's the ammonia bottle. So several 10 ml samples of ammonia were titrated with standardized 0.5A2 instead of sodium hydroxide HCl. Okay, so before I get you too good and confused, all I did here, I'm just saying that for tonight's homework, or even for Tuesday or Wednesday night's homework, we did two titrations. The first time we used sodium carbonate and HCl. The second time we used ammonia and HCl, okay? This question is very similar. They're talking about vinegar and sodium hydroxide, but we used ammonia and HCl. But our calculations will be very similar, okay? So they took vinegar samples and they titrated them with sodium hydroxide, standardized sodium hydroxide. That just means they know this exact concentration because they did a titration and determined its exact concentration. When they did this titration, the average volume of sodium hydroxide used to reach the endpoint was 13.8. So I'm going to skip ahead and tell you that when we did the lab, the titration lab in my kitchen, okay, these were the four trials, sorry, that I did, okay, 4 trials. This one I overshot, okay, so we're not going to include that data. Trial 2, trial 3, trial 4, you're going to subtract the burette readings to find out how much titrant was added. And then you'll find the average volume there. Adding 2, 3, and 4 and dividing by 3 to find the average, okay? They've done that step for us here, okay? They did 3 trials and the average of all 3 trials was 13.8 mils. What is the concentration of the vinegar? Okay, so remember, step 1 over here was to write the balanced chemical equation. So we have vinegar reacting with sodium hydroxide. For those of you who have forgotten, vinegar is CH3COOH, acetic acid. It's reacting with sodium hydroxide. Okay, the double replacement neutralization reaction, which means they split in two and the positive ion from the first goes with the negative of the second and vice versa. Okay, so we end up with sodium acetate and water. Make sure it's balanced, fill in your states, and there's your balanced chemical equation. Now let's fill in what they give us. 10 milliliters vinegar samples. So under the vinegar, I'm going to write 10 mils. Standardized 0.582 moles per liter of sodium hydroxide. So under the sodium hydroxide, that's where they get the 0.582. Average volume of sodium hydroxide, 13.8. What is the concentration of the vinegar? So again, you can see how you have 1, 2, 3, 4 variables and 1 is unknown. Okay, with this question, we had 1, 2, 3, 4 variables, 1 was unknown. Okay, now in this case, we're looking for concentration. In this previous case, we were looking for volume. You're going to do them very similarly. First thing you're going to do is take your 2 knowns for the one sample, one chemical, and convert it to moles. So you have concentration, you have volume. If you want to go to moles, remember we look at this formula, V equals N over C or C equals N over V, however, we want moles, it's going to be C times V. So we start our boxes with volume, start our boxes with volume, start our boxes with volume. There's my volume. All I've done was convert it to liters by moving the decimal 3 to the left. If I have volume up here, I want to make sure I have volume on the bottom. So my concentration, 0.582 moles per liter of NaOH. And again, watch my units and you'll see that they cancel. Liters of sodium hydroxide, liters of sodium hydroxide. So I've taken my 2 numbers and I've multiplied them together to get moles. After I have moles of sodium hydroxide, I want to convert to moles of my unknown. There's my mole ratio step, okay? So if I have moles of sodium hydroxide on top, what am I going to put on bottom? Moles of sodium hydroxide. So you can see how they cancel out, okay? Moles of sodium hydroxide, moles of sodium hydroxide, okay? This middle step is my mole ratio step, okay? Let's just put that here. 1 in front of the acetic acid, there's my 1, 1 in front of the sodium hydroxide. Now in this case, we're looking for concentration. Remember, concentration is moles per liter. Well, we have moles, so where do you think we're going to put that volume? We want concentration, we want it moles per liter. So we're going to have to put that 10 mils on the bottom. So although it looks funky, there still is nothing that goes on the top here. Okay, in this one we were looking for volume, and so we had our concentration 14.8 moles per liter in our last box. Okay, but in this case we're looking for volume, I'm sorry, concentration, so I had to have my volume on the bottom, moles per liter. And then again, take my calculator, 0.0138 times 0.582 times 1 divided by open brackets, 1 times 1, close brackets, equals, and you should get that. Okay, so both of these are the same. Balanced chemical equation, find moles, step 1. Mole ratio, step 2. And then depending on if they're looking for volume or concentration, that helps you determine what you write over here. If they're looking for volume, you're putting concentration on the bottom. If you're looking for concentration, you're putting volume on the bottom. Okay, so homework tonight is it's going to be question number 3, and it pertains to the lab video. So in the lab video, we did 2 titrations. The first one, I was mixing HCl and sodium carbonate. The sodium carbonate was in the Erlenmeyer, and the HCl, there we go, and the HCl was in the burette, okay? And I mixed those 2 together. Now, do this similarly to how I had this one set up. Put your given and your unknown under the appropriate chemical. So, you know the concentration of sodium carbonate because you know you had 1.52 grams in a 100 ml solution, okay? You know that concentration. And you know that you used a 10 milliliter aliquot. You saw me use the pipette and pipette pump to get that 10 ml sample, okay? You know how much HCl volume that you added. That's what this data table is showing you, okay? This is the data I collected from the lab. And then you can use that to find your unknown of concentration of HCl. So take a screenshot of this. This is your homework for Wednesday, this one question, okay? The titration lab procedure that I followed, you can find that on Teams under Files, okay? I use that to get this data. That's what the 35 or 30-minute video is, okay? And then we're going to use this data a second time, or this calculation a second time, in helping us determine the concentration of ammonia, okay? So the titration that we did was 2 steps. First one to find the concentration of HCl, and the second time to find the concentration of ammonia. Okay, so screenshot this, and you'll know we're going to work on this one together Wednesday before we start our organic. But I do want you to do A for homework. Okay, now this slide is just intended to talk a little bit more about primary standards. I talk about it in the video, but I wanted you to see a little bit more info. A primary standard is something that you can make up, and it's readily available in pure form, okay, easy to get. It does not absorb water when it's exposed to air. That's what this little symbol is supposed to remind you of. It's not reactive when it's stored, okay? And it has a high molar mass, so weighing errors are less significant. And I usually use Santa Claus and a newborn baby to help illustrate that. When you were born, most of us were itsy bitsy teeny tiny, okay? I say most of us because one of my children, believe it or not, was 11 pounds, 11 ounces. My smallest was 10 pounds. So, pretty large babies. But anyway, regardless, when they were first born, we were very, very concerned about watching their weight. Same thing with all of you, okay? When you're first born, it's very important that your parents keep track of how much you're eating and of your weight gain or loss to make sure you're getting enough food, because you can't tell us when you're first born whether or not you're getting enough food. Now, let's just say this was a whoops, let's just say this was a 10-pound baby, okay? And let's say the baby lost maybe a pound the first week, okay? That is significant. That's a 10% weight loss, okay? The baby were 10 pounds to start with. Now, let's say we also are talking about dear old Saint Nick, okay? And let's say dear old Saint Nick started off at maybe 300 pounds. Again, I'm just making those numbers up. I don't know how much Saint Nick weighs, but let's say 300 pounds. If he lost 1 pound, that would not cause us as much stress or concern as would a baby losing a pound, okay? Because again, a baby losing 1 pound, that's 10% of that baby's mass, okay? When we're talking about a 30-pound St. Nick, if he were to lose 1 pound, it wouldn't be as significant a worry. So if you have a chemical with a high molar mass and you're weighing it out, and you're supposed to have, let's say, I think the one I used, the sodium carbonate, had a molar mass of 152 grams per mole. And then we were also using hydrochloric acid, which has a molar mass of 34.6. Let's just say I was massing those out, and instead of using 152, I was off by 1 gram and used 151. Compare that to instead of using 36, using 35. The smaller the molar mass, the more significant a difference in molar mass is going to be. All right. So that's why it's important to have a primary standard with a high molar mass, so that if you're weighing it out, making your solution, and you make a little bit of mistake, give or take, of the mass, it's not going to be as big a deal. Okay. So we used sodium carbonate as our primary standard. We put 1.52 grams in 100 milliliters. And you can change that to moles, change that to liters, and figure out the concentration of sodium carbonate. That was our primary standard. Once we knew its concentration, we titrated it with HCl to get its concentration. That was step one of the lab. Once we know HCl's concentration, then we can plug it in over here, the HCl concentration, to find the unknown ammonia concentration. Okay, so again, homework is just to do this calculation. Find the concentration of secondary standard HCl. How do you do that? By following these two examples, 2 and 1. All right, thank you so much. Bye.